Yeah, good afternoon. Thanks to Meena and Rahul for inviting me to present. And so this is joint work with Jailal and Sunil, also from IIT Madras, and I am Balagopal Komarath. Right. So we'll start by looking at some problems between the classes P and NC. So NC can be thought of as containing problems that are easy to solve in a parallel fashion. So what is Lex least maximal matching? Let's say you are given a bipartite graph as input and it has some edges. So the Lex least matching is you start with the vertex 0, let's say on the top half, and you pick the lowest numbered vertex on the bottom half. You go to the next vertex, pick the next lowest available vertex, and so on, and you compute the maximal matching doing this. So the Lex least maximal matching is given such a graph and an edge, does that edge occur in the Lex least maximal matching? So this intuitively this problem seems kind of hard to parallelize, and these are not known to be P complete and not known to be in NC. Right. So I'll define what comparator circuits are. So a comparator gate takes two inputs A and B and outputs A and B and A or B. So it has two inputs and two outputs. Right. And the class CC was defined by Meyer and Subramanian in 1992 as problems log space reducible to comparator circuit evaluation problem. So the output of the reduction is a comparator circuit which only has comparator gates. So I would like to stress that fan out gates are not allowed. What does
it mean, fan out?
It means that you cannot have two comparator gates like this and feed this input to two different gates. Right. Is that clear?
Sorry, I'm missing something.
Right. So let's say you have a comparator gate in the comparator circuit and it outputs A or B, and you have two other comparator gates. So you can't feed this A or B into those two different comparator gates. You need to recompute this A or B from scratch again.
It's like a formula.
Yeah, it's like a formula, but in some sense, some limited form of fan out is allowed because this A and B is being used to compute A and B and A or B. But you can't do that in a formula if A and B are like intermediate values. So it's a restricted form of general circuits, but it could be more powerful than a formula. Right. And pictorially they can be represented like a sorting network. So this is a comparator gate. And so this comparator gate takes A and C as inputs, and it will produce A or C on this wire and A and C on this wire, and so on. So there's a designated output wire, and that's the output of the comparator circuit. Right. Why is this class interesting? So these problems that I mentioned, like Lex least maximal matching and stable matching, are complete for this class CC. So Yeah, and it is known that CC is contained in P, that's trivial, and it's known that NL is contained in CC. So that requires proof, but I'm not going to do it here. So intuitively, CC captures some hard to parallelize problems, but those problems are not like hard enough to be P complete. Right? Okay. There has been some recent work in comparator circuits by Stephen Cook, Yul Filmus, and Manley in 2014. So they show that there exists universal comparator circuit families. So what are they? So if you give, there is a comparator circuit family that when given a description of a comparator circuit and an input to that comparator circuit will output what the input comparator circuit will compute on that input. So given C and X as input, the universal circuit U will output C of X. So that's a universal circuit family. So they show that there are universal comparator circuit families. So U is also a comparator circuit here. And so this means that CC can also be defined as the class of languages that can be decided by uniform polysize comparator circuit families. So it's a computational model. Right. And they also show that closure with respect to EZ0 Turing reductions do not change the class. So it's kind of a nice complexity class. Right. So now we'll just refresh the definition of posets and lattices. So any set with a partial order defined on it is a poset, and if you take any pair of elements and if you look at its LUB and GLB, if it's unique, then that poset is called a lattice. Right. So if you consider the set 1 to I, so this is an example for a lattice. So if you consider the set 1 to I, and if you consider the set of all partitions of I ordered by refinement, it's actually a lattice, and this is called the ith partition lattice. So it's a family of lattices, and the ith one is the ith partition lattice denoted by pi I. So for example, this is the second partition lattice. So you have two elements, and there are two ways to partition two elements, and that's pi 3. So we'll come back to partition lattice in a moment. So these are kind of important. Right. So what we do is we can think of Boolean circuits as working over lattices. So it's like computing over the lattice 0, 1, where 0 is less than 1. So that's the Boolean, smallest Boolean lattice. So we can generalize this by looking at by allowing it to compute over arbitrary lattices. Like instead of 0 and 1, you fix a lattice L, and the constants could be anything from that lattice. Now the and OR gate will compute the GLB and LUB over that lattice, right? And there will be a designated accepting element from that lattice. So the circuit will accept if and only if it outputs that particular element in the lattice. So for example, this is a lattice called the diamond lattice. It has 4 elements, A bar, 0 and 1, and this is a circuit over this lattice. So we have just one gate which computes LUB of its 2 inputs. So this notation means that the initial or the value of this wire is computed by applying F to X1. So when representing Boolean circuits, we usually write Xi or Xi bar. So what I am doing is Xi could be thought of as this function, and Xi bar could be thought of as this function. So what I am doing is I am generalizing this. So at the input gate, we could map an input bit to an arbitrary element in the lattice. So you can see that this will output 1 if and only if x1 and x2 are distinct.
So the same bit can be mapped to different lattice elements in different parts of the circuit?
Yeah, just like you could have x1 or x1 bar.
No, there's only one f.
Oh, the functions could be different. So
Yeah.
This f plays the role of positive or negative. Yeah, each input gate could have xi comma g, where g and xi can be independently chosen. Right. So why is this interesting? So if you look at general Boolean circuits, then this is not very interesting, because what you could do is, given any finite lattice, you could fix some Boolean representation or representation of the elements using bits, and you could compute LUB and GLB using ordinary AND and OR gates. So it wouldn't change the class. Right. So, but it's interesting if you allow restricted forms of circuits to compute over arbitrary lattices. We'll see why. So first we'll do this definition. So for any lattice L and any A element of L, we define this L comma ACC's class of languages accepted by polysize circuits working over L with A as acceptor. So this can be thought of as a circuit over this lattice with 1 as the acceptor, if we want it to accept if and only if x1 and x2 are different. Right. And we can actually the universal circuit family given by Cook et al. Works for any lattice and any accepting element, which implies that this class, the circuit evaluation, canonical circuit evaluation problem is complete for these classes. So the interesting questions are, how will this depend on the structural properties of underlying lattice, and is it possible to always eliminate the dependence on the accepting element? So if you look at general Boolean circuits, it really doesn't matter whether we use 1 or 0 as the acceptor. It's still, if you are looking at uniform circuit families, it still gives the class P. Right? But if you go to restricted circuit families, it could depend. Right. So if L is a distributive lattice, then this class is just CC, so it doesn't increase the power. So that's a consequence of something called Birkhoff's representation theorem. Right. So the interesting question is, what happens when the lattice is non-distributive? Right. And we could show that there is some constant I such that pi I CC would give the class P. So this is independent of the accepting element used. Right. And
So what is pi I?
oh, pi I is the ith partition lattice. So the quantifier for I is the axis. So the axis is a constant I such that pi I CC is P.
What's the constant?
We don't know. Yeah, but pi 2 CC is CC, but there is some constant. And you could also see that pi I CC contains pi I minus 1 CC. Right. So why does allowing comparator circuits to compute over arbitrary lattices help? So is it because of the fan out restriction? Well, actually it's not, because we can show that if you allow arbitrary form or the class of polynomial size formulae to compute over arbitrary lattices, you still get NC1. Right. So fan out is not the only thing here. So this result kind of shows that, and we can generalize this definition to work over posets, and you can actually capture NP as well. But we will not discuss that here. Sure.
Here pi ICC is in P for all I, or?
Yes, since pi I is a fixed lattice. So what you do is you will do the circuit evaluation, and whenever it's so you could put the LUB and GLB table in finite control of the team. Yeah, that direction is trivial. The other one is hard. So just to refresh your memory, the circuit is called skew for any AND gate in the circuit. At most, one of the inputs come from a non-input gate. So this is a standard definition, and we know that uniform polysize skew circuits capture the class NL. So there is a natural way to define skew comparator circuits. So if you take any comparator gate where the AND output wire is used in the circuit, then one of the inputs must come from an input gate. Right. So that's, I hope that's a natural way to restrict. Right, and we can define skew CC as the class of languages accepted by uniform polynomial size skew comparator circuits. So what is this class? This is just a log space. So I'm not going to discuss that proof either. And we can also show that for that same constant I, which yielded pi I CC equal to P, for that same constant we get pi I skew CC equal to NL. So that's just a consequence of the proof of pi I CC equal to P. Yeah, so you can think of L versus NL as a skew version of P versus CC. So CC is comparator circuits, P is Boolean circuits. L is skew comparator circuits, and L is skew Boolean circuits, general Boolean circuits. Right. So I'll just sketch the ideas of this theorem, pi I CC equal to P. So just look outside the box. The red wires are AND output wires, and blue wires are OR output wires. So we are computing 0 and 1, right? And so the output is obviously 0, and you get 2 zeros here. So basically this box is implementing fan out. This is just an example, but it works for any value on this wire. So even if this value were 1, then we would have got 2 ones here. And so the idea is very simple. To implement fan out, you kind of push the fan out logic onto the underlying lattice. Right. So this is a poset here, but it's easy to convert it into a lattice. So what we do is once we get the value that has to be copied, we feed it into a comparator gate with this element X. So you kind of make 2 copies of that value. So if you look at this poset, the LUB of X and 1 is 1 prime, and GLB of X and 1 is 1 double prime. So this 0 prime and 0 double prime are like 2 copies of 0, and then you design the lattice such that this sequence of LUB and GLB operations with Y, Z, W. So what you want to do is you want to convert this 0 prime and 0 double prime back to 0 and 1. So you can do this kind of computation again and again. Right. So this poset does the job, and yeah, and how can we convert this into a lattice? Right. So there is something called Dedekind-McNeil completion, which says that every poset can be can be embedded into a lattice while preserving all existing meets and joins, or LUBs and GLBs. So we only used LUBs and GLBs that were present in this poset. Right. So this is the completion of that poset into the lattice. Thanks. Right. But we are not done, because this is kind of an arbitrary lattice and it's not clear. So if we change the accepting element from this one to some other element, it's not clear whether the class would remain the same or not. So there is this theorem by Pudlak and Tuma, which says that if any given finite lattice can be embedded into some partition lattice. This kind of says that partition lattice, the family of partition lattices are universal, right? So what we can do is we can embed our finite lattice into some partition lattice, right? And we can build our comparator circuit over it. Right, and then we can apply this theorem. So partition lattices have this nice property. So what's this property? I'll just intuitively explain. There is a formula. So for any element in that partition lattice, there is a formula that, when applied to some input value, will tell you whether that input value is greater than or equal to A or not. So this one is the maximum element of pi I, and this 0 is the minimum element of pi I. So what this formula does is it tells whether x is greater than or equal to A or not by outputting a bit. You can think of this as a bit. Right.
When you say this, the formula is on pi I, meaning it's using only the meet and join operations of.
Yeah, correct. Yeah, so it can be implemented by a comparator circuit too. Right. So if you look at this lattice, it only outputs 1 or 0 because it's directly simulating the Boolean circuit. So our comparator circuit over that pi I will output some A or some B. I mean, it will use some particular element in that lattice to accept, and it will, when it rejects the input, it will always output some B. And we know that A is greater than or equal to B. So this is from that reduction. And if you apply this formula on the output of that comparator circuit, then we will get either 1 or 0. Right, so we have converted that A or B to 1 or 0. Right, and since the accepting element in the Boolean circuit doesn't matter, we can also get a comparator circuit that uses 0 as the accepting element. So which shows that the accepting element doesn't really matter. Or we can simply say pi I Cc equal to P. Right. So I'll explain this using a figure. So this is what Berkhoff's representation theorem says. We have a distributive lattice here, and I have labeled the elements using finite sets. And if you look at it, the LUB operations are simply union on those finite sets, and GLB operations are simply intersections. So you can kind of see that those are easy to implement in a comparator circuit. So if the maximum size of these sets is k, you can encode these elements by the characteristic vectors of corresponding sets, and then you can compute union and intersection using a comparator circuit. Right. So that shows that for any distributed lattice, irrespective of the accepting element, we get the class CC. So the a question would be, so we use the poset to show that arbitrary lattices could capture P, right? So is it possible to embed that poset into a distributed lattice? Actually, if we apply Birkhoff's this theorem, we can show that that poset cannot be embedded into any distributed lattice. So I'm not going to present the proof, but the idea is we use a proof by contradiction. So if it were possible to embed that poset, then we could label the elements of the poset using sets, such that GLB and LUB should be satisfied by intersections and unions. So you would get a system of equations on unions and intersections, and there would be a contradiction there.
So is it true that no poset which implements fan out can be embedded into the discrete lattice?
Yeah, we would like a theorem like that, but we don't have it yet. Right, so this is your question. So we have shown that there is a non-distributed lattice that can capture P, but is it true for any non-distributed lattice? That's if you take any non-distributed lattice n and any element as the acceptor, then can we prove that it's equal to P? Right. So there is an interesting fact about non-distributed lattices. So if you recall, this is pi 3, more popularly known as M3, and this is another lattice called N5. So there is this theorem which says that any non-distributed lattice must contain one of these lattices as a sublattice. So to show this, it's enough to show that either this or this can simulate P, right? Right. So that's an open question. What is pi 3cc? Would it give P? We can show that this does not depend on the accepting element used. That is independent of the element used for accepting the set. This class remains the same, but we don't know what this is. It's a superset of CC and a subset of P. That's all.
So if you knew what pi 3cc was, that would classify all lattices, all comparator circuits.
Yeah, right. So. Yeah. No, but you still need what? So it will yeah. Yeah, because it could be that N5cc is not equal to P, but if you show that pi 3cc and N5cc are equal to P, then yeah, then there's a dichotomy theorem there. Right, yeah, thanks.
Questions where we particular sets. So what about depth of comparator circuits? Like what's known about that?
I don't think anything has been studied.
So the summation of NL and CC, that's like what's the depth of that?
It requires depth, the order of the edges, or number of edges in the graph. Yeah.
So was the only thing that's non-constructive in the proof of the existence of such an eye, the inside Goodluck's thing?
Yeah, correct.
That's the only.
Yeah. So that theorem, I haven't read the full proof. It's a long proof. So, but it's highly non-constructive. Like one of the open questions is, if you take the dual of pi 4, is it contained in pi 2 to the 100 something? So.
and Balagopal